So this is the third of our statistical bivariate tests that we're going to learn about, and today we're going to learn about Anova. Anova is an analysis of variance and test of significance that is appropriate in situations where we want to examine independent variables with more than two categories, such as social class or race and ethnicity would all have two or more categories. So social class could be working class, middle class, and upper class. And race and ethnicity could be Anglo, African American, Asian American, etc. So the logic is the same as a t-test that you learned about last week. It's just extended to independent variables with two or more categories or samples. And remember, a t-test is when you have two independent variables that are interval or ratio measurements. So one way Anova, which is what we discuss here, is analysis of variance procedure using one dependent and one independent variable, or a bivariate analysis. So examples are, is there a relationship between religion and support for capital punishment? So religion would have multiple categories of that. Is there a significant difference between racial groups on the basis of educational attainment? Again, racial groups would have multiple categories such as African American, Asian American, Latinx, etc. So the logic of Anova is we're asking, are the differences between the samples large enough to reject the null hypothesis and justify the conclusion that the populations represented by the samples are different? We are not asking, are there differences between the samples? So a null hypothesis is going to have the mu1 equals to mu2 equals to mu3 to mu k. So the logic of Anova continues. We treat the total variation in a set of scores as being divisible into two categories. So there will be a table or output in SPSS that says variation within groups and variation between groups. The variation within groups, the distance or deviation of raw scores from their group mean, and variation between groups, the distance or deviation of a group means from one another. So what this does is it compares both of those. The test compares the amount of variation between categories with the amount of variation within categories. So if we look at this chart, you can see that the mean on the left-hand side, top left-hand side, with lower class, the mean at x1 is measuring the variance between x1 that's within the same category. So the variation within the same category, because both of those are in lower class. If we go to the second bell curve, which has working class above it, on the top row, we have mean x2 and the arrow between x2 and the mean in that working class. So that's between groups. If we continue, middle class is between groups. Mean of x3 to the point x3, so it's still within the same curve. And upper class is the mean of x4 and the area within the same upper class bell curve. If you look at figure 8.2, this is a graphic representation of variation between the four groups. So we have variation between x1 mean, which is the lower class mean, to working class mean, which is x2, to middle class mean, which is x3, to the upper class mean, which is x4. So that's between the groups. See, it crosses over the bell curves. Figure 8 1.1, they all stay within the same bell curve. Figure 8.2 is between all four different bell curves. So the sum of squares is an important part of analyzing Anova. Each of the types mentioned below represents the sum of squared deviations from a mean. Total sum of squares, the sum of the square deviation between each individual score and the total mean. Between groups, sum of squares, the sum of squared deviation between each group mean and the total mean. And within groups, sum squares, the sum of the squared deviation between each individual score and its group mean. So for a calculation between group sum of squares, the SSSB between groups, it tells us the difference between the groups. It measures the variation in scores between categories. So we sum up the n and we square the means, the overall mean minus the individual mean, and nk, subscript k, and the number of cases in a category. Xk is the number, the mean of a category. So within group sum squares, so that means that they're all within the same bell curve. This tells us the variations within our groups. It also tells us the amount of unexplained variance. So that is the sum of xi minus the mean of x subscript k all squared. So nk is the number of cases of sample. K represents the number of different samples. X subscript I means the mean of a sample. X subscript k equals each individual score in a sample. And so then we total the sum of squares, and that means this is the total variation of the sum of squares, or SST equals SSB plus SSW, and the equation is sum of x squared minus nx mean squared. So if we want to look at the mean square between, it's the estimation of the between group variance obtained by dividing the between group sum of squares by its degrees of freedom. Again, the pesky degrees of freedom coming back from the chi-square. And the mean square between is a sum of squares between divided by the degrees of freedom between. And where the degrees of freedom between equals the degrees of freedom between. And dfb equals k minus 1, where k is the number of categories. So mean square within is an estimate of the within group variance obtained by dividing the within group sum of squares by its degrees of freedom. That equals SSW divided by degrees of freedom within. And you can calculate that as n minus k, and n equals the total number of cases, and k equals the number of categories. The F statistic, which we saw in the t-test, is the ratio between group variance to within group variance, and is calculated by this, mean square between divided by mean square within. Definition. So F ratio, or F statistic, is used in analysis of variance. The F statistic represents the ratio between group variance to within group variance. F obtained is the test statistic computed by the F ratio for between group or to within group variance. F critical is the one that you want to have over with the alpha level in this class of 0.05. The F score associated with a particular alpha level and degrees of freedom. This F score marks the beginning of the region of rejection for our null hypothesis. And so if we looked at a researcher is interested in comparing the educational attainment of different groups, black males, Latino males, black females, Latinx females. So the hypothesis is that there's no relationship for the null, and for the working hypothesis that there is some kind of relationship that divides these four different categories. So you can see from the table on the right hand side that they've calculated out all the things you need to calculate to be able to make a determination. So again, here's our favorite 5-step model. Step 1, making assumption and meeting test requirements. So in this Anova, we determine independent random samples are used. The dependent variable, years of education, is interval ratio level variable. The population is normally distributed, and the population variances are equal. And then step 2, stating the research and null hypothesis, selecting the alpha. Again, the alpha is going to be 0.05. In this class, there's no relationship between independent and dependent variables. And for the working hypothesis, at least one mean is different from the others. And step 3 of the 5 model, selecting the sample distribution and specifying the test statistic. So the sampling distribution for Anova is the F distribution, whereas before in the t-test we saw it was a t-test distribution. So the sampling distribution equals F distribution. We have an alpha of 0.05. We have degrees of freedom within. For this example, it comes out to 17, and degrees of freedom between is coming out as 3, and F critical is 3.20. So just like on a t-test, if it's above the 3.20, then we know it's statistically significant, and the alpha will be below 0.05. So step 4, we compute the test statistics. So you have SS between and SSW. So that's 10.61 divided by 2.67, and you see that F is 3.97. So we make an interpretation about this, and we see that in the alpha distribution, where the F statistic is an alpha of 0.05 and a one-tail distribution of F in this table. So we have 17 and 3, and you can see where degrees of freedom between, degrees of freedom within. and we obtained 3.63, and our critical F was 2.84, so we know that this is statistically significant, and its p-value is below 0.05. So the critical 2.84 was the shaded area, and everything after that, or higher, right, is statistically significant. So since the obtained F is beyond the critical F value, we reject the null hypothesis of no difference, and we find support for a working hypothesis. So step 5, we make a decision, which we have done for like the last 3 slides. Make a decision interpreting the results of the test. We reject the null hypothesis of no difference and conclude that people are different in their educational attainment. Our F of 3.97 obtained is greater than the critical value of 3.20. So this is how you would run it on an Anova and SPSS. You compare means, you do a one-way Anova. In this example, it's TV hours, factors, degrees. You want to do descriptive statistics and continue and click OK. And then this is an output that you would get. So you need to check whether the difference among the means are significant in the Anova table, which is at the second table, where you would look at the SIG column, the most right-hand column on the second table, and it's 0.000, so that tells you that it's below 0.05, so that also indicates that it is statistically significant. We also need to check sample sizes to make sure there are enough people in each group. So then the N has to be greater than 30, and the only one that comes close is junior college, which is 32, so we can check that off. And we need to check the standard deviations to make sure none are very different. And we can see that we have a high of 4 and a low of 1.33. So the Anova table reports a significance level of 0.000. In other words, it's highly unlikely that the differences in the means occurred by chance, and we may conclude that there is a relationship between educational attainment and TV viewing. In other words, as you will find out later, or you can look at the mean, the more education you have, the less likely you are to watch television per hour. So if you have less in high school, you average about 4.61 hours of television a day, and if you're a graduate person, a PhD, master's person, then you average 1.79 hours per day. So then if we did a multiple comparison of means, which is asked of you in the homework in one of the labs, so this is the Tukey's HSD honestly significant difference. So on the left-hand side, you'll see in some cases it may be necessary to determine exactly where the significant differences lie. So is it really in the less than high school, or is it really in the graduate level of the TV hours where the difference lies? So we can make a multiple comparison after a significant F ratio to pinpoint differences. So the equation for Tukey's HSD is what you see on your screen, where Q is the table value of a given level of significance for the total number of group means being compared, MS within groups mean square obtained from the analysis, and then group number of subjects in each group assumes the number in each group. So I have run, or you can run, the Tukey, which is a post hoc test indicated which group means difference from one another, which is an important refinement of the analysis, and you do that by using a post hoc multiple comparison command. So here's an example comparing TV hours and numbers or levels of education. So we're going to focus on the mean difference column, which is the third-ish column where it says mean difference I minus J. And we can compare the two groups. So let me point out first that the column that says SIG, S-I-G, tells you whether the p-value of the comparison. So the first row where it says less than high school and comparing it to high school is statistically significant. So those who have less than high school, when they are subtracted from the average mean of high school graduates, they watch 1.627 hours of television more, and it's statistically different than the less than high school is statistically different than the high school students, high school graduates. And if we look at less than high school and junior college, less than high school watch over a little over 2.1 hours of television more, and they have a sig or a p-value of 0.004, so that's statistically significant also. And then if you compare less than high school with a bachelor's degree, less than high school watches 2.502 more hours than a bachelor's degree, and their p-value is 0.000, and we know that anything below 0.05 is statistically significant. And then we have less than high school compared to graduate, and they watch almost 3 more hours less than high school students watch almost 3 more hours than a graduate student, and their p-value is 0.000, and we know that anything below 0.05 is statistically significant. If we go to the second row, which starts with high school, and we look at high school compared to junior college, high school is only watching about a half hour more of television junior college, and the p-value is 0.901. That's way above 0.05, so we know that it's not statistically significant. So basically a high school person and a junior college person are watching about the same amount of hours and are not statistically different at all. And if we look at high school and compare it to bachelor's, they watch almost an hour more, high school graduates, but the p-value is 0.07. That is slightly above 0.05. It's not statistically significant. This suggests that high school and bachelor graduates are basically watching the same amount of television, and it's not statistically different. So positive mean differences indicate the first group has a higher mean, and negative mean differences indicate that the second group has a higher mean. And if you want to do this, you can look at the left-hand bottom and determine how to run the analysis. Analyze, compare means, one-way Anova, dependent variables, statistics, descriptive, and then Tukey, continue, OK. So graphing, I'm not going to ask you this class. Bar charts allow us to quickly compare the means of different categories. They're placed on the horizontal axis, so you can compare them. We can see that the respondent's highest degree and the number of hours watching television, and you can see that the less than high school watches the most, whereas the graduate folks watch the least. So if we're reading the research literature, here's an example of mean scores and results in analysis of variance for the various scales. So if we have self-image scales, and we have we're comparing 3 different groups, and we can see the F statistic is statistically significant. We can also see that blacks, in this case on the first row of negative self-images, have a higher mean than the other 2 groups. Positive self-image, the whites, the Afrikaans-speaking whites have the highest mean on positive self-image, and we can also see this as ethnic identification. So if there would be a table, you would want to figure out if the F statistic is statistically significant, and then you can also look at the means differences related to the 3 groups in this table, for example. Here's another one where you have women's college females, co-ed college males, and co-ed college females. And we can say that for the first row, for example, co-ed college males had the highest mean, 9.56, with active task behaviors. And then if we look at group type column, we can go all the way down to the 3rd row where it says counter arguments, where we have a statistically significant result. And that appears to be the only statistically significant result in this table thus far. But again, the point is you can compare those 3 different categories of women's colleges, co-ed college males, and co-ed college females, and make a determination where the difference specifically lies in the means. Alright, so if we want the requirements for using the F ratio, we compare between 3 or more independent means, and we have interval data or ratio data, random sampling, a normal distribution, equal variance.